we always knew we had to do something about PLC security, and this just seemed something so clear.
Welcome everyone to the Industrial Security Podcast. My name is Nate Nelson. I'm here as usual with Andrew Ginter. He's the Vice President of Industrial Security at Waterfall Security Solutions, and he's going to introduce the subject and the guest of today's show. Andrew, how are you?
I'm well, thank you, Nate. Our guests today are Sarah Fluchs, the Chief Technology Officer at Admaritia in Germany, and Vivek Ponnada. He's a Senior Customer Service Leader for Gas Power at GE in Canada. And they're going to talk about a new report, the Top 20 list of Secure PLC Coding Practices. The list was put together by a group of individual volunteers, and Sarah and Vivek were two of the leaders of the group.
Okay, let's get into it.
So Sarah and Vivek, thank you so much for joining us. Before we dive into the details of PLC coding practices, can you tell us a little bit about yourselves, please?
Yes, so I am Sarah Fluchs. I am the CTO of Admaritia, which is a German OT security consulting company. And my background has always been in automation engineering. So I'm an automation engineer turned into security. So that's things that are close to these specialties in automation are always the things that are most interesting to me and things that are close to engineering methods. And next to Admaritia, I'm spending a lot of time in standardization in ISA. For example, I've recently been appointed to the ISA Standard and Practices Board, which is something which I think is a great honor. But important for this project is that it's not a standard, but a community project and something that can go way quicker than a standard can go.
My name is Vivek Ponnada. My day job is as a service manager for General Electric in the gas power business. And my background is industrial control systems and cybersecurity in the OT space. PLC programming, I was a field service engineer for several years, and then I was a solution architect for turbine compressor controls upgrades. So it was great to be part of this community project where my technical skills were kind of put to test and gathering all the good information from several PLC experts in the field. So thank you for having us, Andrew.
Before we dive into the details, maybe start with you, Sarah. Can you give us an overview of the project? What are the top 20 list of secure PLC coding practices? Where did it come from and what have you got in there?
Well, I think the important point is to mention that it was all sparked by Jake Brodsky, who held a S4 talk in 2020, before the pandemic kicked in, on secure PLC coding practices, which was one of the talks that I think a lot of visitors to S4 had highlighted in their conference programs because it was so clearly necessary. Because we all know PLCs are insecure by design for a long time. And we all know there are things like secure coding practices in normal IT. We know that from normal software pretty well. And we always knew we had to do something about PLC security. And this just seemed something so clear and so hands-on to do. So that was something that drew a lot of people's attention at S4. And right after S4, I think even at the same evening, I had a conversation with Jake about how we should make something out of it and turn it into something that people can work with. So we started thinking about that, and later on, Dale Peterson, the organizer of S4, kicked off that project, saying, okay, let's really do this. Let's create a quick turnaround top 20 list of secure PLC coding practices. And the idea really is to not just copy what we know from secure coding practices from other industries for normal software, but to try to create something that works for PLCs to make the coding more secure, whatever that means. I think we're going to dive into that later on. And at least make them the most secure they can be, given all their particularities and sometimes vulnerabilities that we have to live with.
And Vivek, did you want to add anything there?
I think Sarah covered the primary goal. It was to kind of focus on the level 1, Purdue level 1 devices, where historically there was not a lot of focus on security. So the intent is to say, while these PLCs were not built with security in mind, there are things that can be done by programming them differently or by alerting on certain functionality that's natively available in these controllers. So that was the intent of the project, to say, there are things we can still do to improve the security posture at the level 1.
Right. So it's really a list of of exactly 20 secure coding practices. In the middle, we sometimes had doubts that we would end up with exactly 20, but we did in the end. And it's a short list. So there are 2 ways to dive into that document that you can download for free at plc-security.com. And the document consists of 2 pages, which are really an overview of all 20 practices and a really short summary. So a title and a short summary. It's something that you can stick to the wall next to your PLC programming engineering station or something. And then there's a longer part that is a deep dive into each practice, where we give more background about why this practice is necessary, what security goals it achieves, implementation guidance, how to actually implement a practice, examples, either how to implement it or what could happen if it's not implemented. And also mappings to other standards or frameworks to show that we can interact with other standards. We've got a MITRE ATT&CK mapping, we've got a MITRE CWE mapping, we've got a 62443 mapping. So it's not something just out of the air, out of the blue, that stands there for itself, but it of course has its connections to other references. And all this detailed material is, I think, about 40 pages long. So average of about 2 pages per practice. And that is where all the detail goes, and where we're still looking for improvement. So anyone who wants to comment on that and has better ideas and or wants to add code snippets or examples or anything that can be added. And we also provide a comment form on plc-security.com that you can download and where you can comment on practices in an easy way.
Andrew, if I recall, we did an episode with Jake Brodsky not too long ago.
That's right. That was just after, I think, S4 2020. We interviewed Jake. He talked to us about consistency checks. When you're programming PLCs or you have, systems of multiple PLCs, if one PLC reports that a pump turns on and the other PLC reports that, there's no water flowing in the pipeline, there's a problem. So he talked about, some of his ideas for what made sense in terms of secure PLC programming. I have been through it to a degree. I mean, I haven't studied it obviously as thoroughly as you folks have, but I had a bunch of questions. Can I start with, let's say rule number 8, validate HMI input variables at the PLC level. And then there's a couple of other rules on 11 and 12 that talk about sort of sanity checks on values in the PLC. Does this flow rate make sense? Does that instruction make sense? This, in a sense, it flies in the face of common, programming wisdom. In the enterprise space, for example, if I have a web-based application for booking, classes for preschoolers, and I go into my Oracle database and I tell the database the age on the participant record. These preschoolers have to be between 4 and 6 years old. Don't allow any other age. And then a month later or 6 months later, I add another function. I add another class for teenagers. And now all of a sudden the Oracle database is malfunctioning because the 3 to 6 year old age is not intrinsically associated with children, which the records are modeling, the participants. It's associated with the application. If you put too much application knowledge into the database, if you put too much application knowledge into the PLC, instead of into the HMI where all the other application knowledge is. Are you not asking for trouble down the road when you change the application subtly and now suddenly all the PLCs stop working?
See, I think the example that you gave is probably not the appropriate or apt example here, because the HMI is not hosting the application, to be honest. The HMI is primarily a viewing software, right? It's hosting the operator interface. It's kind of displaying the values for the operator. It's also allowing entry. So if the operator needs to adjust something, there's a button there that they can click and enter 4, 6, any of the values that you mentioned. What this practice number 8 is trying to explain is you have the controller that's running the code, that understands the process, that has all the inputs and outputs, and the HMI should be a viewing software, should be an entry point for the operator to manipulate values. However, if you use the HMI, and increasingly there's more capability on HMIs because all the software is now quite capable of adding code similar to adding code in the PLC. So over time, the HMIs got more and more involved with coding. So if you but if you have software in the HMI that has this operational value range or any of the code that should be in the PLC, what ends up happening is you miss the software testing capability, you miss the rigorousness with which PLC code is tested, and you end up with code in 2 different places, essentially nullifying any security benefits you might get by first focusing at the PLC level and also being able to test it and standardize it and program it with security in mind. So the intent behind the number 8 is to sort of codify what's been widely known for a long time. However, we still see examples of this being a problem. For example, the Oldsmar, Florida situation recently, where while we don't know all the details, it's likely that the HMI software allowed for entering a significantly higher value than what's reasonable, what's possible in the process, or what's programmed in the PLC. So this particular practice is just trying to codify that HMI should be able to access only variables at a certain range, which you can adjust. In your example, if a year from now, 2 years from now, the batch process changed or something else fundamentally changed, you can adjust that value to now be restricted to another set of values, but it should be a valid range for what you're trying to accomplish.
And also, one of the real important parts about number 8, so it's called validate HMI input variables at the PLC level, not only at HMI. And I think one really important part to stress here is the not only at HMI part, so that you really keep things the PLC can do best within the PLC, because it's technically a device that is made for understanding the process, and we just need to use that knowledge and make use of that. And many PLC programmers are not even aware that this could be a security feature, so that you can do some input validation and some monitoring, but you don't actually need any more extra devices. But for some things, the PLC really is well equipped to do that by nature, because it's just what it's supposed to do.
In a sense, I dived maybe too fast into the details there. Can we back up for a second? We're talking about how a PLC can contribute to security. We've got one example in front of us here. Does it fit into a high-level philosophy? How should a PLC be contributing to cybersecurity?
One really important part of PLC security. So one thing that a PLC really can do for security, we've talked earlier about what does a secure PLC code mean? So what is security in PLC programming? Which is also a question that we try to answer with our project and with the top 20 list, because everyone says, well, PLCs must be programmed more securely, but what can a PLC do and what can't a PLC do? And that is actually something we see a lot of controls or a lot of coding practices that actually aim at integrity. And the example you picked is also one of a prime example that aims at integrity, because that really is something that a PLC is equipped well to do. And that can be done at code level pretty well. So you can validate inputs to ensure integrity. And you can use the alarm settings that a PLC has and the flags that a PLC has for security benefits. So this is why I think a third of the whole list is dedicated to integrity, because this is just something that a PLC can really achieve well regarding security.
So Nate, let me paraphrase real quickly. That was a complicated question with a complicated answer. What I heard was that the checks that it makes sense to put into the PLC are the checks that reflect knowledge of the physical process. So, for example, if there's a new pump installed, and the pump has a different operating range than the old pump did, then it makes sense to update the PLC, because the PLC is the computer that is physically connected to the pump. The PLC is the computer that, in a sense, understands the most about that pump. And so it makes sense to update the programming in the PLC to say, these are the new safe operating range for the pump. If you get a command to operate the pump outside of this range, reject that command, because we don't want to damage the pump physically. And so it makes sense to encode the knowledge of the physical process into the PLC and give the application programmers sort of an extra level of confidence that no matter what mistake they might make at the application layer, the PLC will reject commands that are dangerous. A couple of the rules use the word alarm. And, a lot of the rules seem to imply the ability to do some kind of alerting. If you discover that someone is trying to write an out-of-bounds value into a PLC register, if you've done your different kinds of sanity checking in the different rules here, the PLC figures out there's a problem. But how does the PLC notify anybody else that there's a problem? I mean, I'm not a PLC programmer, but I have written a bunch of communications drivers, Modbus, for example. That's sort of the by far the best known PLC programming interface, or not programming, but communications interface. Modbus, the base standard, there's lots of extensions, but the base standard lets you read values and write values. And that's it. There's no concept of alarm in Modbus. If a Modbus PLC figures out that something fishy just happened and wants to raise an alarm, how does it raise an alarm?
That's a good question, Andrew. In the process industry, people are quite used to this concept of alarms. In fact, historically, we had big panels, annunciator panels, that sounded an actual alarm with a big blinking light, as well as a horn on a speaker. So in the more modern PLC and HMI world, when a PLC has something out of range or wants to indicate to the operator that something is wrong, we actually code these specific alarms in a controller to then communicate that to the operator on the HMI interface in an alarm page. So a typical operator station has a section for an alarm, or maybe they have a separate display that just shows nothing but alarm. So those are tied to highlighting to an operator that something is wrong or something needs to be attended to. So in the process industry or power plants or oil and gas installations, it's fairly common. People understand the concept of an operator receiving an alarm. So in most of these practices, we try to explain that you need to code one of these alarms. Now, ISA 18.2 has a much more rigorous definition of exactly what needs to be an alarm, what's actionable, what an operator should be seeing versus what's just logged. So we kind of use some of those terminologies here interchangeably, because our intent behind these practices was to communicate to those process industry personnel, not necessarily security personnel. So we kind of use the word alarm or log in an interchangeable manner, but the key intent there was to say, hey, in the PLC, use the functionality to then alert the operator. Does that answer your question, Andrew?
So if I've understood you correctly, you're saying the PLC would figure out something's wrong and would write, let's say, a 1 into a register whose meaning is this alarm was just raised, and the HMI would poll that register from time to time. And when it sees it go from a 0 to a 1, it puts an alarm record up on the alarm interface, on the alarm summary. Is that what I heard? You'd use a PLC point to communicate the alarm?
Yeah, I think in a big picture manner, that's exactly how it works. So essentially, in the PLC code, a bit flips from 0 to 1, and that is already pre-coded to show as an alarm on the operator interface.
Yeah, well, also what you notice when you look at the PLC practices, and I think that corresponds well to your question, is we've got a lot of practices in the end of the I think from practice 16 or something, which are monitoring practices. So you have things that say, okay, summarize certain values and trend them on the HMI, and that is exactly that. The HMI, of course, keeps being your window into the process, and it's better equipped for making things visible and visualizing them. The important part just is the PLC is more reliable in tracking these values and improving and validating these values, and the HMI is there for visualization. And of course, it's also important to know what values. I think it's the same on a smaller scale with PLCs and HMI, like we see in monitoring and SOCs and so on. You've got a lot of values that you could monitor. The question just is which are the important values to monitor from a security standpoint, and which values that are maybe totally normal to monitor, like uptime or cycle time. That it could be done. It could be that it's totally normal for many PLC programmers to monitor these. But the important point here is to raise awareness that a change in cycle time, for example, could as well mean a security-related issue, because if code changes in the PLC and the PLC program changes, cycle time, so the time that the PLC needs to calculate and execute the program, changes as well. And since a PLC is so deterministic, so normally the cycle time is really steady over time. If it changes, it could point to a lot of errors, but it could also point to a security incident where someone changes code in the PLC.
Waterfall Security Solutions is the OT security company. If you're wondering what is the difference between a unidirectional gateway and a firewall, or a so-called unidirectional firewall, then you'll be interested in Waterfall's latest ebook. Firewalls are used throughout both industrial networks and enterprise networks. But best practice demands something stronger, something truly unidirectional at the IT-OT interface. To see the difference that unidirectional security makes, please download the free ebook, Firewalls versus Unidirectional Gateways, from the Waterfall website under the Resources menu.
I like that answer. I mean, one of the things I like about the answer, Nate, is the word security versus the word secure. I mean, I forget, Sarah or Vivek mentioned the insecure by design problem a couple of answers ago. The PLC programming document is talking about secure PLC programming practices. The word secure, the word insecure, the opposite of insecure is secure. Insecure by design is an initiative that is arguing for encryption and password protection on PLCs. But my point is that the opposite of insecure by design is secure by design. So once you have encryption and passwords, the implication is now we're secure, but it's not. The concept is good, but the terminology is confusing. To say that, if we follow these 20 secure programming practices, then we have a secure PLC. That's not true. We're talking about improving security. We're talking about making things more secure. We're not talking about becoming secure. There's no such thing.
That's fair enough, Andrew. Although, give me the scenario here. So if I have encryption, if I have authentication on PLCs, in what sense am I not then secure?
Well, you have to think about what kinds of attacks are encryption and authentication designed to prevent. They're designed to prevent what's called technically man in the middle, but classic example. Let's say a bad guy has managed to break into something in the OT network. They've managed to break into a printer. Modern printers run Linux under the hood. They're into the printer and they're in programmer's heaven because they got a Linux operating system. They're hacking. They can reach out and connect to any PLC they want to. in an insecure by design environment, they can connect to any PLC they want to and tell that PLC whatever they want to do, and the PLC will do it. Doesn't challenge you for a password. That's the kind of attack that the authentication and encryption is designed to address. Here's a different attack. Get your malware running on the HMI workstation. Watch the HMI screen, learn how it works, and start pressing buttons on the HMI, just like we saw in the Oldsmar, Florida attack. And now the HMI program has already logged into the PLCs, is already got encrypted connections to the PLCs. Whatever you do on the HMI is going to be transmitted through encrypted connections into the PLCs, causing the physical process to malfunction. So, this is my point. Encryption and authentication are good things, but they're not a silver bullet.
Okay, Andrew. So if we take the global view of things, do we have any sense of what percentage of the world's PLCs have encryption, have passwords already on them?
I think the answer is almost none. Now, some of the new models of very popular PLCs have those features available. A fraction of those PLCs, when they get installed, have those features enabled. But the vast majority of PLCs that are in use have been in use for at least 3, 4, 5, 10, 15 years sometimes. They don't have these features, and they certainly don't have them enabled. So percentage-wise, I don't know what the number is, but it's almost all PLCs are insecure by design in terms of not using passwords and authentication. But in a sense, we've digressed here. Let's come back to the programming practices. We've digressed into encryption and authentication. That's not the focus of the programming practices. The focus of the programming practices is what you can do inside the PLC. The focus of this other term that we've been talking about, insecure by design, is what can you do at the interface, at the communications interface. But we're going to come back to Vivek and Sarah here and talk about what we can do in the PLCs. I was going to ask you about the cycle time stuff. Cycle time, you suggested track uptime, track hard stops, track memory usage. If you see changes, then clearly something has changed. And in a changed control environment, this is potentially a threat. You want to understand why has it changed, and if there's no apparent reason, dig deeper. But how do you track this? So, for example, let's say you did historize cycle time, or let's say you historized memory usage. And in normal operation, there's a memory usage spike once every 3 minutes when operation X occurs, because it happens once every 3 minutes. But if someone looked at the chart, you'd see that something suspicious has happened, and now there's 2 spikes every 3 minutes, the normal one and a smaller one when a piece of malware is running. It's one thing to say, let's historize this so we can see this. How would you actually see it? In order to see it, does the operator need a procedure to say once a day, once a week, once a month, go to every PLC and look at the cycle time and see if it's changed from a month ago? Or is there something automatic you can do? Is there an alarm you can set up saying we've got a different memory usage? It's great to say this is a forensic tool. I can look back and see when something changed. But actually seeing that something changed, how do you do that?
Boy, that's a great question, Andrew, because when we use this term operator, in a lot of these cases, we actually mean 2 different people. One is the physical operator that monitors alarms and monitors the process. But there's also the controls or process engineer that's actually coding the software and monitoring the process in a different way, right? They're the ones that is tuning the process, configuring the PNID portion of the controllers. So if you take this example of the memory, an operator that does a process operation could be least bothered by how much memory a PLC is consuming, because that's not their job, right? Their job is to monitor the process and make sure the process is running safely and efficiently. So in a lot of these PLC monitoring use cases, what is being recommended by the top 20 list is log them and trend them on the HMI so that maybe it's not as obvious to a process operator as to what the level of detail is and what's exactly going on, but all they need to be aware of is that something is different. And then they alert the maintenance technician or the process or controls engineer, who will then dig deeper into what's going on behind the PLC cycle times or the memory usage.
Let me ask you a question about cost. I've looked through here. There's two costs that sort of leap out at me. The simple one is if we add a bunch of additional points or registers to a PLC to produce an alarm or two or three or maybe 4 or 5 different kinds of alarm, a consistency alarm, a bounds check alarm, different kinds of alarms for values that are being written to the PLC, or that the PLC is observing, saying there's an inconsistency between these two values. You're adding a whole bunch of registers. With some of the products out there, in particular the historians, you pay for points. If you want to track these alarm registers in the historian, and I'm guessing you do, you've got to pay for more points. So that's an extra cost. And in a sense, more fundamentally, writing this code in the PLC is a cost as well. Someone has to write the code. It's more code than in an insecure PLC. And in my understanding, at least some of these markets are extremely price competitive, because the whole goal of a lot of modern automation is increase efficiency. And, efficiency is measured in terms of cost benefit. Benefit being what comes out of the process. Cost is everything that goes in. If somebody comes in and proposes, let's say there's a bid out saying, I need someone to program 37 of my PLCs for a factory expansion. And someone comes in and bids, I'm going to do this the right way. I'm going to use the secure coding practices. I'm going to write more code. It's going to cost you more. And someone else comes in and says, I'm not going to do any of that. I'm going to do it the old insecure way. And I'm going to write less code. And I'm going to be able to underbid the person who's doing it the right way. Doing it the right way seems to put you at a competitive disadvantage. Is this something that you guys have thought about?
Yeah, definitely, Andrew. The cost that you mentioned is multifold, right? There is a certain cost to utilizing the functionality that's available, but kind of thinking this through carefully and configuring the alarms or properly coding it the way that's described in these practices. But there's also a cost to not doing it, right? So when something does happen and it's very hard to decipher exactly what went wrong, there is no log, there is no alarm for whatever went wrong. So there is a significant cost at the back end where you could have started the plan back up in a safe manner in 2 hours versus now it's taken an extra day to troubleshoot and figure out what went wrong. So there is the front end cost of actually configuring and properly programming the PLC versus being able to maintain this code over a long period, over 20, 30 years, and also being able to do forensics when something did go wrong. So you're right that upfront there is an additional time cost, which is more, because actually configuring the alarms or adding some points, there is very minimal cost in these practices because, unlike 20 years ago when, PLC alarms were costly because they were a restricted number of alarms you can configure or restricted points you can add. In fact, the ISA 18.2 that I mentioned was required because now an average PLC or DCS has way too many alarms. So the number of alarms is less of an issue, the type of alarms and what needs to be carefully programmed, that takes time. So the biggest investment, the biggest cost of incorporating these secure PLC coding practices is time during engineering. Now, part of that engineering time can be cut down when code is standardized, right? So if you're talking about gas turbines, for example, where a lot of code is standardized, you apply, the same type of code from one project to the other. So there is no additional cost on future projects once you have standard code. Similarly, at any big EPC level, when they're doing a plant level design, once you code to a certain standard, you can replicate the code going forward. So there is no additional cost there. However, if you're talking about an upgrade project, if you're doing a brownfield upgrade to a certain PLC and you have to incorporate these secure PLC coding practices, there is that additional time that is required upfront, but that has to be kind of balanced with what costs you're saving over the life of the project in being able to understand the PLC operation better, so that you can quickly replace a component if something was wrong, or troubleshoot and be able to come back up safely if an incident were to happen down the lane.
So these are good points, and I want to add only two things from another perspective, maybe. If you think about cost for PLC security, first, I think it's important to mention in your overall ICS security program, probably PLCs are not the first devices to tackle. Because obviously a PLC won't save you from ransomware. No PLC coding practices won't have. They are not there to eliminate Stuxnet-like attacks. So that's all not the things that can be achieved with just PLC coding, just secure PLC coding. But it's something like to add on a more advanced level, right? So it's good to have it as a last line of defense, and it's good to have them in your calculation. It's probably not the first thing you do in an ICS security program. That said, if you have an ICS security program and you want to do something for security, there are way more expensive things to do than to have some small little twitches in your PLC programming. Because PLCs you have anyway, you need them anyway, and chances are that many of the top 20 secure PLC coding practices, if you're following good coding practices, you probably implement a lot of them anyway. You just don't use them for security purposes. And it's probably way more costly to try and achieve the same things that we achieve here in PLC coding, just for PLC security, not for the overall program, but for example, things like integrity checking, having a last line of defense, like for what Vivek said, the Oldsmar incident where PLC values were changed to values that should have been detected by a PLC easily, but weren't. Things like that are way more easily prevented in a PLC than in some extra controls or extra devices you're adding on top of a PLC. So you don't need, for some things to monitor, you don't need an expensive SOC and you don't need extra monitoring devices. For some things to prevent, you don't need extra devices, but you do have the PLCs. And for some things to validate and to integrity check, you don't need extra cryptographic mechanisms, but you can use what your PLC already offers. So that is something, of course, doing the top 20 is more costly than not doing them. At least the tendency is there. But in terms of overall cost in a security program, that is, I'm sure that's not the most important, not the most expensive part of programming, of ensuring security, because so many other measures you could take in a security program would be so much more costly.
Andrew, we've discussed this before maybe, but at any given site, there are a lot of PLCs, right? As Vivek's talking about, like the time it takes to apply any change across so many devices might be significant. If we could use an example, maybe, how many PLCs might one find at, say, a refinery?
Yeah, it really depends on the physical process. A small manufacturer who produces 1,000 custom parts a year for some other manufacturer might only have one or two PLCs. A refinery, refineries can be massive. Rule of thumb is that at a large refinery, you're looking at maybe a few 100,000 PLC registers, PLC points that you're tracking. Each PLC tends to have let's say between 1 and 300, or maybe a big one between 1 and 500 physical measurements, physical points and registers that it's tracking. Do the math. That's going upwards of 500 to 1,000 PLCs at the site. So if you're going to reprogram 1,000 PLCs, it can be costly. But what I heard in the answer was that there's obviously life cycle, long-term benefits that might persuade owners and operators to specify, I want this stuff done, even if it costs me a little more upfront. And there might even be some short-term benefits that reduce your, let's say, deployment costs for a new function in your physical process if you do things the right way, because certain kinds of errors are detected faster and you actually save time. So that was my next question. Let's go back to Vivek and Sarah and see what they have to say about operational benefits. I remember I interviewed Jake Brodsky at S4, was it a year ago, 2 years ago? It was 2 years ago. And one of his examples was, one of his points was operational benefits. Are there operational benefits to this security? I mean, one of his examples was, if you're doing a little sanity checking and you say, I'm going to ask the PLC 3 miles down the road whether the water pump is running. And if it says, yeah, the water pump is running, I'm going to compare that to the state of my flow meter. And if the flow meter coming into the reservoir here says there's no water running, that's a problem that deserves to be alarmed on, because it's probably one of three things. Either the application has changed and something is broken in the application, and it's the wrong pump I'm querying, or the application isn't working anymore, and we need to diagnose that instead of just silently failing and wasting engineering hours trying to figure out what's going on. Or something fishy is going on. There's a cyber attack underway faking some of these values. Or there's a hole in the pipe and there's a geyser halfway between here and the pump with water shooting into the air, and that's an operational problem that ought to be alarmed on. Are there operational benefits to this sort of degree, this intensity of consistency and bounds checking?
You're raising one of my favorite points about this entire project, Andrew, because, of course, the answer is a big fat yes. Because that's one of the good things about the top 20 practices, that in many of the cases, operational benefits and security benefits are so close together and almost indistinguishable from each other. And that's a good thing, because we have this often quoted balancing problem that we have between security and between comfort, or between usability. And in these cases, that's actually not the case. But what's good for operations and what makes operations easier and makes operations more comfortable, actually in many cases also benefits security. And I think these are the type of controls and the type of measures that you should aim for in a security program anyway. So everything that you can do, and that is something that you can do way better in ICS security than in IT security, because of the nature of these of the devices that you're operating. For example, the PLCs, they are deterministic anyway. They are not that complex anyway. So a lot of things that reduce complexity and improve maintainability and improve bug hunting in PLCs actually have to do with limiting complexity, with modularizing, with documenting things better, with using the right registries for the right things. And these are all things that are good coding practices. They make coding easier, they make maintainability easier, they make operations easier, and they make bug hunting easier, regardless if the bugs have security nature or are just normal operational bugs. And this is something I think there's this really special and really good direction of this project. And there's something that you can see in the PLC coding practices. If you go to the more detailed section, you see that each of the coding practices has a subsection called why. And this why we detailed what we think a certain practice has benefits for. And it's always security in there. But there are always the two other questions. Is it beneficial for reliability? And is it beneficial for maintenance? And many, many, many of these practices really have benefits for both.
So you mentioned the MITRE framework a little bit earlier, and you've correlated each of these programming practices to the MITRE attack framework for ICS, presumably. I don't understand that correlation for some of these rules. So, for example, the very last one, number 20, says, look, if you have a condition, if you have A and B and C true, then it means this thing has happened. And you should report, the tank is full or the tank is overpressurizing or something. And it seemed to say that if you had an attack that caused this undesirable condition and then wrote a 0 into the alarm register saying, and, the conditions occurred, but there's no alarm, you would want a sanity check saying, I just wrote a 1 into the alarm register. Is it still an alarm? And if it's not, you would have a second register that says, the first register has gone inconsistent. It's supposed to reflect the state of the world, and it doesn't. And you raise another alarm saying something fishy is going on. I don't understand the attack model. If an attacker can mess with the registers to cause a problem and can write into the alarm register saying, nah, there's no problem, can it not also write into the sanity check register saying, nah, it's all consistent? I don't get what we're preventing in some of these. I don't understand what capabilities we think the attacker does or does not have that these programming practices would get around.
Yeah, I think you bring a really good point here, because what we're trying to do is to add another layer that is typically not present in these PLC programs, right? Typically, PLC programs are written very efficiently. You do whatever minimal is required to send an alarm to the operator. Here we're, just like you described, asking for an additional configuration to double check that the first alarm is accurate. And you're right that a sophisticated adversary might then manipulate the second register as well. So the layer that you plan could be defeated. But essentially, it's about layers of protection. You're just trying to say it's unusual to have the second level of protection, so why don't you add it? So it doesn't prevent the attack from happening, but there's high likelihood that the adversary might not be aware of the second register being configured or the second alarm being available, because that's not usual.
Sarah, Vivek, this has been great, but we spent a lot of time here sort of diving into the details. Before we wrap this up, is there a topic that you wanted to get to? Is there a question I haven't asked that you want to address?
One thing that I think in the project, we need to understand this was a community project. So everyone who wanted to take part took part. We had on the platform where we started this project, we had over 900 registrants, and a large portion of them read and commented and voted for practices. And since we didn't require them to provide much information about themselves, being security people, we're information sensitive, for example, of course, but we don't have a good overview of where they came from in case of in terms of user group, target groups. So were there vendors or integrators or service providers or asset owners? But I have the feeling that we have a lack of vendors raising their voices in this. And this is something that I would be really interested in, understanding what vendors think about these practices and if they maybe, and I think that's something that differs from vendor to vendor a lot, if they already implement lots of the practices, if they think some don't make sense because they have other things that they already implemented, or if they maybe implemented things but didn't mark them or didn't identify them as security relevant, because these are things I think that are maybe all the vendors are doing things like this, but they don't communicate it well if they do. And that is something that I would like to change, that we get into conversation between asset owners and vendors, and that vendors get more transparent about what they are actually doing in terms of security in their code, because a lot of the times the vendors obviously have their code in in modules, and it's not supposed to be changed a lot by integrators or by asset owners. And in these cases, we really rely on the vendors being transparent about and talking about what they do in terms of security and how they understand security in PLC programming, because that is something that I think has been missing in the conversation so far, and I really hope some vendors are going to reach out as well.
Yeah, I want to add maybe a couple things, Andrew, if that's okay. I want to use a car example. Maybe it's crude and rudimentary, but the modern PLCs have a lot of functionality that is rarely used. So we're using these modern PLCs like we use these older PLCs in the past. So a lot of industry professionals have not really upgraded their skill set because it works, right? So it's kind of like, you got 7 gears in this new car, but you're just operating the first 4 because that's what you're used to. So the why part, like why would anyone want to incorporate these practices? The one request I have is we're not asking for a complete rewrite of how things are. All we're saying is, these modern PLCs have a lot of functionality inbuilt in them. And oh, by the way, be a little bit more methodic in your programming, so that you can help in instant response, so that, you're not always playing the victim card when something does go wrong. There are things that the PLC has that you can enable, that you can configure. And if you did, you're able to then figure out what's wrong, both for maintenance purposes and also for security purposes, so that you can bring back the process up in a safe manner in a relatively shorter period, compared to saying, I don't know what went wrong, or having to restart the process all over again because you thought you fixed it by downloading a new code, but then it's still unsafe because something is still wrong. Malicious actors in the system, and you're not able to take that bad code out of it. So the why part is, this is 2021. We're talking about security at Purdue level 2 and above. We have been talking about it for a long time, but we never really focused on Purdue level 1 and below, because historically we said there was no security there. So we've asked a lot from vendors, and vendors have delivered by improving a lot of protocols and hardware available with security functionality. But because the user base has remained where they were 10 or 15 years ago, most of the newly developed functionality remains unused. So in a lot of these use cases, all it is saying is, let's use that functionality, or let's repurpose that maintenance-driven functionality for security, so that we can do IR better, we can do forensics better. So the key as to why anyone should consider using all or some of these programming practices is, we then will improve our security posture at the plant level without needing a lot of new gadgets, without needing a lot of external devices, because these PLCs are now very different. They have so much more functionality than they had in the past, but we continue to not use them or underutilize the available functionality, which is what we're trying to fix with this practices list.
Sarah and Vivek, thank you so much for joining us. Before we let you go, is there a thought you'd like to leave with our listeners?
Well, obviously for me, the most important thing is, again, this has been a community project, and there's only flourishes if it stays a community project. So we have a small core team that is a handful, or maybe 2 hands full by now, of people who care about this project, and we want to make it as open as possible. There is a maximum permissive license placed on the top 20 PLC coding practices, so you can download them for free, you can use them, you can spread them, you can share them, you can talk about them, you can change them, do whatever you want. The important thing really is to get the word out that something like top 20 secure coding practices now exist, because they didn't before. And we really like to ask you, if you read anything in there and you don't like it, or you think you can do it better, please reach out. We do have a comment form, and if that's not intense enough for you to comment via a comment form, really, we're not a closed club, so everyone is welcome to join our core team and determine the strategy where the top 20 project is going. We have so many open issues that we want to tackle. We could think about PLC environment practices. We have a CWE MITRE collaboration that we are thinking about. And there are so many other ideas, adding code snippets, providing virtual PLCs for trying things out. And if you are passionate about any of these strategies and adding these, please join us, because we can always use more passionate people for PLC security.
I agree. And from my end, my request to the end user base, the end user customers that are looking at these practices list, please share it with your vendors. Please share it with your integrators. Similarly, if the security people on the call can share it with their OT counterparts, the ICS process engineers, they'll get the right kind of feedback as to how it's applicable to their process or not, or how they can achieve it with a future upgrade or maybe in the existing system. So the intent is to kind of spread the word out, have more and more people look at these practices and give us feedback on how relevant it is to their process and what we missed, so that we can improve the practices and we can create a better list so that we keep it up to date and more relevant to what's appropriate for security and maintenance in the current process world.
And also, don't keep this in the security bubble. This needs to go to engineers, because to the people who actually program the PLCs. It's important that people in the security bubble know about it and they know it exists, but it's also important that it's harder to reach these people, the security information, to get this to the engineers.
Andrew, how about a parting thought from you?
A couple of things. One is, don't misinterpret me. I asked a bunch of hard questions here just so that we could dive into the details. It's not that I'm critical of the document. I like the document. I think it's got, good practices that we should all be using. In particular, I dwelt on costs at one point in the interview. To me, what I think we're looking for is evolution. We're looking for use the first version, evolve this into a second version, get it to the point where it's close to standard, and then get the vendors involved. There should be standard function blocks that the vendors provide. They provide lots of standard blocks for lots of functions. Add a bunch of these security and sanity checking functions so that we don't have to write a whole bunch of new custom code in every PLC that we want to do this for. We just use the vendor's standard blocks and spin them together, and now this functionality pops out at a much lower cost, and we can reap the security and operational benefits because we're leveraging the vendor's investment in the technology. So, I think it's a great step forward, and I encourage everyone to read it at plc-security.com.
Great. And with that, thanks to Sarah and Vivek for speaking with you, Andrew. And as always, Andrew, thank you for speaking with me.
Always a pleasure, Nate. Thank you.
This has been the Industrial Security Podcast from Waterfall. Thanks to everybody out there listening.